Hi, welcome to Module 3 of Lecture 14. So in the previous two lectures we dealt with derivatives of functions of more than one variable, but these functions were all scalar functions. One might ask what to do if you have a vector-valued function. Recall that a vector-valued function was one that had multiple components as part of a vector. So if it were a function of multiple variables, the function itself is a vector. So this would be something like this, where you had f1 of x and f2 of x, and so on down to the nth component. And that's it. So this is a vector-valued function. We dealt with this in the very first module of the previous lecture. So now the question is, how do we take a derivative of this thing? Well, you might imagine that since each one of these components can be differentiated via a gradient, then all you have to do is do the gradient n times, and you'll be right. In fact, all you're really doing here is taking the gradient n times. So let's say you have, to be more specific, a vector-valued function that mapped the real numbers, m dimensions. So the input, there are m variables, to the real numbers with n dimensions. So n-dimensional Euclidean space, so you map m-dimensional Euclidean space to n-dimensional Euclidean space. And therefore, the function itself is a vector with n components, and x, which is the argument of the function, has m components. Well, then you would imagine for each component of the function, the gradient would have m components, right? So for each fi, the gradient should have one component for every input variable, for every part of the argument, so it should have m components. Well, now you have n of these things, right? f1, f2, down to fn. So the total number of derivatives you're going to have to take is m times n. So that's a lot. That can be a lot if you have a very high dimensionality function with a high dimensionality argument, but typically you don't have that big a thing. Anyway, point is we have to do something with these if you want to take this derivative. What do? Well, as we learned in the previous part of the course, we can keep track of a lot of different things in a matrix. So that's what we do. We define the Jacobian matrix, J, such that J sub ik, so little j here is the, perhaps confusingly because we often use j as an index, but little j here is the an element of capital J, the matrix, and the ikth component of the matrix, right? So the ith row, kth column, is going to be equal to the partial derivative of the function I, the ith component of the function with respect to the mth variable. That's it. The mth argument. And that's it. So you would make your whole Jacobian like that. For instance, if you had a if it was two-component function with two arguments, then this would be df1 dx1 df2 dx1 df1 dx2 and df2 dx2. That'll be it. So there's the Jacobian, so the Jacobian matrix. Where is this? Why would we actually care about this type of thing? Well, one reason is it comes up a lot. Well, it comes up sometimes when you're dealing with multidimensionality in the implicit function theorem, when you're trying to implicitly differentiate a function. That we'll talk a whole bunch about in the very last lecture for this course. And there you will see again the Jacobian matrix, and also often its determinant, J, which is often sometimes called the Jacobian, even though it's the determinant of the Jacobian matrix. The reason is you'll much more commonly see the Jacobian determinant, the Jacobian matrix's determinant, than the Jacobian matrix itself. So we tend to use a shorthand to call this the Jacobian, even though it's confusing. Sorry, I did not make that up. So that's the Jacobian matrix, and the Jacobian matrix determinant, also called the Jacobian. And that's the primary use you'll find of it. There are other uses as well, though. If you recall, we talked about the Taylor expansion a few times now. Well, if you had a vector valued function, you could take the approximation of that by using the Jacobian matrix like so. So there, this is very similar to the gradient. The gradient, in fact, if you noticed, the gradient, and I should have erased that, the gradient of let's see, each row of the Jacobian matrix is actually the gradient for a component of the function. So this over here in red is the transpose of the gradient vector for f1, and this one down here in blue is the transpose of the gradient vector for f2. And if you had more components of f, you would have more of these rows. So basically this whole thing ends up being gradient. So if you notice that, if you take the first, if you take your very first row, right, and then you multiply it by this column vector here, what you get is the same thing as the gradient dotted with x minus a. So if this is only a single component function, it'll be the exact same expression as we saw when we used the gradient to take the Taylor expansion, to approximate the Taylor expansion of a scalar valued function of more than one variable. This is a generalization of that to having multiple components of your function, to having a vector valued function. So this is another potential use of the Jacobian matrix. In general, the Jacobian matrix just represents change on multiple dimensions at once. It's a little harder to have intuition for, but it's when you have a vector valued function, it represents more than one thing at once, and the Jacobian gives you changes along multiple dimensions at once. And that's pretty much it. We're going to do one quick example to give you a sense of how this works, although it should be pretty similar to what you've seen before, and that'll be it for the Jacobian. So, quick example, let's make up this one here. So f1 should be x1, x2 minus x1 squared, and f2 will be the same thing, except it'll be minus x2 squared. So this is sort of a complementarity with cost argument. Okay, what's the Jacobian? Well, we gotta fill in all these elements. df1 dx1 is this first one with respect to x1. So that's gonna be x2 minus 2x1. Remember, this is a partial derivative. The next one upper right is going to be df1 dx2, which is just x1, because everything else is constant, and the only x2 is actually in the first term. df2 dx1 is going to be this one with respect to x1. The only x1's over here, so this is x2. And the last one is df2 dx2. The only there's two x2's, it's symmetric to the first one, so you have x1 minus 2x2. And there you go. There's the Jacobian matrix for this vector valued function. The determinant, which you often want to use, would be x2 minus 2x1, x1 minus 2x2 minus x1 x2. And there you go. That's the entire thing for Jacobians. There's nothing else going on here. Frankly, they're not used very commonly in political science, which is one reason why this is in the second part of this two-part lecture, effectively, about multivariable calculus, not in the first part. But there you go. In the next one, lecture, we're going to talk about higher order derivatives, second order partial derivatives, and introduce the Hessian, which is used more frequently. Thank you very much.